This video will discuss the solution to question 33. The memory chip shown in figure 6 requires that node X settles to at least 80% of the readout voltage before activating the sense amplifier in order to avoid wrong operation due to its noise. How much time since the activation of the word line is approximately needed for node X to settle to 80% of its readout voltage? Assume R1 is 1 kilo-ohm of the excess transistors, CS is 10 femtofarads, CB is 100 femtofarads and VDD is 1 volt. Hint: use approximations. And then 8 possible times are given. So to repeat the question, we're going to look how long it will take for the voltage at this node to settle at 80% of its readout voltage. And to do that, we're going to look at the circuit that is formed by our storage capacitor, our parasitic capacitor and this access transistor. We can model this transistor when it's turned on by the R-on resistance, and that'll give us the following circuit. We need to look at the time-dependent behavior at node X, which is equivalent to this node right here. This here is node X. And we can do that by computing the time constant in this node. We already have the equivalent resistance, which would be R-on, but we don't have some equivalent capacitance, because in past that will be RCB, but we also have this CS. And to do that, it's important to remember that the ground is in fact one big node. So these 2 points in the circuit are connected. So what we can do is model it as the following. And again, this here is our node X. And we want to know the time constant in this node. For that we use the R-on resistance and the equivalent capacitance formed by these 2 capacitors. We will call that equivalent capacitance CEQ. So like this. And the computation of an equivalent capacitor of 2 series capacitors is done in the same way as we compute the resistance of 2 parallel resistors. So it is CS times CB over CS plus CB. And if we do that and we fill in the given values of 10 femtofarads for CS and 100 femtofarads for CB, that gives us approximately 9.1 femtofarads for this equivalent capacitor. We can then compute the time constant as R-on times our equivalent capacitance, which is 1 kilo-ohm times 9.1 femtofarads. And that is 9.1 picoseconds. We can now look at the time-dependent behavior of this node. We will model the behavior of the voltage in node X as a first-order step response. And the time-dependent function for that is given on the formula sheet and is the following. The voltage at time is infinity was computed in question 31 and was found to be 545 millivolts. Now, plus the voltage at time 0 was also given, that's the pre-charge voltage, so that is VDD over 2, or in other words 500 millivolts, and then again minus 545 millivolts multiplied by that exponent here. Okay, so this is equivalent to 545 millivolts minus 45 millivolts times that exponent here. Now the question that we're asking is at what time we will reach 80% of the settling voltage. And by that we mean at what point have we settled for 80%. So the difference that we see from 0 to infinity is 45 millivolts, because at the beginning we have 500 millivolts and then when the circuit has settled we would have reached 545. So the voltage, or our delta voltage that we want to see for 80% would be 0.8 times 45 millivolts, and that is 36 millivolts. That means that we need to find the time at which this voltage reaches 500 plus 36 millivolts. And we can do that by setting up an equation that looks like this. We need to solve this equation, and we can just do this by subtracting this from both sides. So that is negative 9 millivolts is equal to negative 45 millivolts times that exponent here. We can then divide both sides by negative 45 millivolts, and that'll give you e to the power negative t over tau is 9 over 45, and that is 0.2. And then we can solve this by taking the natural logarithm of both sides. So that'll give us negative t over tau is the same as ln 0.2. And now the only thing we have to do is solve for this t, and that gives us negative tau ln 0.2. The only thing we now have to do is fill in our tau that we found before, and that was 9.1 picoseconds according to our calculations. And if we now evaluate this, you will get that that is equal to 14.6458, etc. So approximately 15 picoseconds. And that's the correct answer.